So those who are joining us virtually due to illness and other things, hopefully you're doing well, hopefully you're recovering. But we just talked a little bit about variance on the board, and all of what we covered is really in the slides, which are all on Piazza. So you can look into the slides, learn more about variance, and we're going to go through them now just as a review, a rehash, so to speak, of what we already covered. So these slides are all about variance, and before we get into the review content, well, I have an idea. Let's go through the slides again, and then we'll do the mini quiz, and then we'll take a break. So I think that's going to be good, since we're talking about variance already. So just this is review for people. It's always a good idea to review. One thing that we talked already about is how likely is one thing relative to another thing. So we talked about variance, or we talked about probability distributions. We talked about PMFs, PDFs, and so forth and so on. That's the first thing we really covered. And then we talked about what on average means. So we talked a little bit about this notion of an expected value. We called it E of X, and that E looked really fancy, and that X was capitalized, and all those things had some meaning that we talked about. So the example would be, what's the average support for impeachment, or what's the average support for a specific policy? So that's the thing we did next. And then we talked about how to break probability down by support, not only overall, but also conditionally. In other words, not only support among everyone, but also support among Democrats. So that's the second thing that we did. And this was called conditional probability. And you can also define something called conditional expectations, which are defined in the same way. We'll talk a little bit more about those next time. So these are the three things that we've done already. But this isn't a sufficient toolkit for understanding the social world, because we want to know not only about what's the average or how likely is one thing relative to another thing, but we also want to learn a little bit about how to characterize uncertainty or some notion of spread around the mean and so forth and so on. So this is what we've been discussing already today for those of you who are just joining us through the video recording. But we're going to briefly just to show you the slides one more time. Then we'll go through the mini quiz, and then we'll do the break, and then we'll come back together. So we've talked a little bit already about the first moment. That's the expected value. So the expected value, I've written out the formula here, and we've talked about it. But the first moment only characterizes the general tendency of the data. We might sometimes want to go beyond the general tendency to explore and explain other aspects of the data. Other aspects like the spread around the mean. And that's what we've already done with the variance, but we've written it down in the slides here too. So the second moment is going to characterize the general spread around the mean. And when we're talking about what are called moments are just the expected value of that random variable to some power. We'll give a general definition in a minute. But we're basically saying, like, what's the average value of not only x, but also x squared and x cubed and x to the power of n in general. So we have different moments. There are different varieties of moments. There's the raw moment, which is just the expected value of the random variable to the power. But there's also something called the centered moment, which is what we did with the variance. And that's the expected value of x subtracting off the mean. And that's important for what we already discussed. There are other moments too, like the third moment, which characterize the skewness. These in general aren't super important to everyday research, but it's just something that we'll introduce here. And there are several different varieties of kind of higher order moments. So there's the kind of first moment, which is the expectation, and there's the second moment, which is, you can think of it, the centered version is the variance, and then there are these so-called higher order moments beyond the second moment, which characterize other aspects of the data. So the idea here is a question, comment, yeah.
What do moments mean in this context?
Yeah, so moments mean the expected value of x to some power. So we're or some version of something like this. So the expected value of x raised to some power, or some version of it, and we'll talk about three different versions. The raw moment, which is just this thing here, or the standardized moment, which is when you subtract off the mean and divide by the standard deviation, or the centered moment, when you just subtract off the mean. So there are three different kinds, at least, of these moments. As to why they're called moments, I don't know the history of that, actually. Maybe someone in the room knows. It's a good question. We'll have to look that up for next time, or maybe if you're on the link, you can put a comment about why it's called moments. But there's also something called the moment generating function, the function that generates the moments. We're not going to talk too much about those today, but it's there. It's there for you if you want to talk about it. So in general, we have the raw nth moment, the standard nth moment, and the standardized nth moment. And in general, we don't really think about moments beyond the fourth moment, which is characterizing something called the kurtosis. We usually think about the first moment a lot, because that's the average, the weighted average, where the weights are equivalent to the probabilities. And then we have the second moment, which is going to, especially the centered version of it, which is going to tell us something about kind of the distance, the average distance between the random variable and the mean of that random variable. And then we have the third moment, which characterizes skewness. We're not going to really do a deep dive into why that is. You can think about it intuitively in terms of different powers. So if you take something and square it, squaring it it's a symmetrical function. So negative things, positive things are treated in the exact same way. Like x, 2 squared is the same thing as negative 2 squared. It maps in some symmetrical fashion. Whereas when we're talking about the third moment, this isn't a symmetrical function. It's sort of like an S-curve type of idea. So when you take x and you subtract off the mean, you're actually, and you take the third power, you're actually you're upweighting and downweighting, or I should say, things that are above the mean and things that are below the mean are going to be handled differently, because taking something to the third power doesn't generate a symmetrical output. Whereas when you're taking something to the second power, it does generate a symmetrical output. So that gives you at least some intuition for why the third moment tells you something about kind of the skewness of the distribution. We're not going to cover that too much, but we're talking about it now just to sort of compare and contrast the different moments. We have the first moment, we have the second moment, we have the third moment, then we have just higher order moments, which we're not going to talk too much about, but maybe in the problem sets or maybe in future work you'll see it. And then this is the example that we already talked about. How do you define the expected value for, or I should say the variance for the Bernoulli random variable? And we talked about how we can find this using that LOTUS idea, the law of the unconscious statistician idea, where the expected value of some function of x is just that weighted average, the weighted average of the function of the different possibilities. And you can use this same idea to compute these higher order moments of the random variable, like the expected value of x to the n. You might ask yourself, how do we compute that? And the answer as to how we compute that is you can use the same idea that we had before. So this is giving you some sense for different moments, different ideas from that. And this is just going through that example again. And we have that quantitative reasoning question as to why p minus p squared is always going to be greater than or equal to 0. And these are all things that we've done. In the last slide here, 8 out of 8, the last slide in this set is just the following. And this is something that we'll return to. So this is just an introduction. Like if you go to the restaurant, you'll get an appetizer first. So this is the appetizer version of something that's going to come up later on. And what this basically tells us, this slide is just giving you an appetizer version for the connection between the variance and the percentiles of the distribution. So the idea behind this is basically the following. We have our normal distribution, and it turns out that in the case of the normal distribution, the variance equals sigma squared, where sigma is one of the parameters of the distribution. In other cases, that's not true. So in something called the gamma distribution, the variance is a complicated function of multiple parameters. But it just so happens in this special case of the normal distribution, the variance is equal to sigma squared. And what we have here is a characterization for the normal distribution in terms of different kind of groupings, where we're basically saying take mu and then subtract off one standard deviation, which is just the variance, the square root of the variance. If we subtract off the variance and then we add the variance, that creates a certain region. That region is encompassed here where my mouse is trying to point. And it turns out that 68.26% of the data, or 68.26% of the probability mass, or 0.68%, or 0.68, fraction of the probability, so to speak, fall within this range. And we could do the same thing by saying what fraction of the data, so to speak, are going to fall within 2 standard deviations of the mean. So we're going to subtract 2 sigma on the left here, and we're going to add 2 sigma on the right over there. And we're going to ask ourselves the same question. what fraction of the data, so to speak, are going to be encompassed within this interval. And when we're using the normal distribution, we can use the mu and we can use sigma to compute those. 95% of the data is actually encompassed within that range. This 95% of the data idea is going to come back to enlighten us when we're talking about hypothesis tests. Like, you can ask yourself the question, why is the significance level 0.05? And it actually connects to this idea of 95% of the data in some intuitive way that we're going to explore a lot more later on. So this is presaging for the future, really. And we can do the same thing by saying what fraction of the data lie within a 3 standard deviation interval from the mean. And the answer there is it's about 99.72% of the data, which we'll make the idea more precise later on. But this is getting to the idea of percentiles, getting to the idea of mean, connecting it with standard deviation, which is just the variance, taking the square root of the variance, and we're connecting it all together in a kind of graph or visualization that will come back to further enlighten us later on as we go through the semester. So this is really just presaging for that. And I should pause now. This is the last slide here for today, but we'll go to the mini quiz and then we'll do the break. But are there any questions? Are there any comments? All right, I see no questions. So now let's just go to the mini quiz. And if you could just answer to yourself these mini quiz questions, we have 5 of them. Then when you're done, we'll take a break and we'll come back together at about 1:50. So we'll take like 9 minutes of doing this plus break, and then we'll come back together and then we'll talk about these questions. So take some time. We're just gonna be silent together. Think about it for yourself. Since the midterm and the final exam are going to be you working with yourself to solve the questions, you won't have a pair, you won't have a team necessarily. So it's important that you check your understanding in a few different ways, and this is one way we'll check it. So we're just going to take some quiet time for you to think through these 5 questions, and then we will go from there. You don't have to calculate anything unless you want to. Just think through, like, what would you do, and your answer will be words, but this is just one way of sort of checking your understanding or checking things that we need to review for the class. So that's what we'll do for the next few minutes, and we'll come back together at 1:50. pause on it. If you're not done, that's totally fine. But if you do want to take like a 1 or 2 minute break, we could do that now too. Then we'll come back together. I suppose we can start talking a little bit about what people think. Does someone want to talk a little bit about maybe the interpretation of the question? Since half of these questions is just the interpretation, once you get the interpretation, usually the answer falls in an evident fashion. But does someone want to talk a little bit about what they thought for question number 1? And what's the interpretation, or how do you find it? Yeah.
My guess was, because it's always a guess, was that it's asking for the PDF. So I looked up what the equation was for the PDF for the normal, and then I was like, I would just plug in the mean and the standard deviation into it. But I didn't do that because it didn't say I had to find it. So I didn't.
Yeah, exactly. These are designed just to be more like thought questions. So you could either, there are tables which contain these probabilities, or in general you'd be using R, and you'd basically say, well, let's find the PDF of this distribution, and let's throw in the value of 2 into that PDF. So that's exactly right. So what about the next question? So it looks very similar. I like to do trick questions because they're more thought-provoking. So this is a bit of a trick question, but it looks almost the same. Does someone want to talk about what's different and what's the importance of that difference? Maybe let's skip to the third one, then we'll come back to this one. So what about this? Oh yeah. Yeah. What makes you say cumulative?
The second one? No.
Because it says PR, that's why.
Yeah. Yeah, so this is the probability. Well, so what's the probability? Another way of saying it is just, what's the probability that x equals 2 if x is this normally distributed random variable? Well, what are some things we know about normally distributed things?
So I guess it was around 68%, like it would be a little less because the mean is 0.2 and the standard deviation, this is the standard deviation squared, so it would be probably more than that.
Yeah, I like
it would be 95 because it would be like 2 standard deviations above the mean, so I was like...
Yeah, I really like the reasoning there. I think that would be a great way of attacking it if this, instead of an equal sign, was a less than or equal to sign. Yeah, so here, think of the equal sign, think of the probability statement. So there are a few things that we know about this, yeah. Other takers. So remember the distinction between probability and probability density? Do you remember? Yeah, so for this one, it's actually, there are a few ways to do this. So first of all, you could use this idea that we talked about, using CDFs to compute probabilities. And we could basically say, the probability of falling within an interval is equal to the probability of kind of the upper end CDF minus the the lower end CDF. So we have this difference in CDFs to try to compute probabilities. Here, there's an equal sign there. So in the context of the normal distribution, the probability of taking on any specific value is 0. Remember the distinction PDF versus PMF, discrete versus continuous. It's one of those subtle things that we've been talking a little bit about, but we're talking about it again. So it turns out that the probability of any specific value for a normal distribution is 0, because that the continuousness of real numbers, how there's an infinitely many numbers between any number and any other number. When you're talking about real numbers, that kind of complicates things, and that's why the probability of any specific value is 0. The probability density, like we talked about in the first question, that's not equal to 0, but the probability is equal to 0. So there's a subtle difference there. So this was a trick question.
So whereas in the next question, you can really use in between, it has a range.
Yeah, exactly. So in the next question, there's a range, and this range is what allows you to get a number that's not 0. So now we're asking, what's the probability of falling within this range? So does someone want to talk a little bit about what they thought for question number 3? Yeah, what are your thoughts?
I would calculate the CDF of it being less than 2, and then subtract off the CDF of it being less than 1.
Yeah, exactly. So, and I haven't maybe emphasized this to the extent that I need to, but if we want to understand the probability of lying within an interval, we basically say, what's the probability that you're below the upper end of the interval? And then you basically say, well, if you look at like just some random distribution, if you look at a distribution that looks like this, there's the upper end interval point, and then there's the lower end interval point. So this is the upper end point, and this is the lower end point. And we're basically saying, what's the probability of falling within this interval? This is very similar to what we were just talking about with our discussion of variance and percentiles and all those sorts of things with the normal distribution. But now we're asking, what's the kind of the probability of falling within this interval? And the way that we calculate that is, in this case, we can take the difference between the area to the left of kind of U and to the left of L, and that gives us this remainder area in between the two. So the area to the left of U is all of this, and the area to the left of L is all of that. And the difference between the two is this middle area, and that middle area is what we calculate as the probability using the CDFs together. So in other words, it's the area in the middle, and you can use the CDFs to calculate it. You can also use summations or integrations in a specific way that the slides went through a little bit, but this is the toolbox idea or approach for how you would get this probability being within this range. Any follow-ups to that? Any questions or any comments? All right. So there are no questions. You'll get some practice with this, so you'll really understand it, even more than you do now after the next problem set. So, with this material, if there's one level of understanding, but then there's the next level of understanding, and then there's even the level beyond that, and it's just like layers to an onion. So right now you're at one layer, and after the problem set, you'll be at another layer. So what about this question? This is a more conceptual question, and I'm not expecting you to do the calculation, but just in big picture terms, does someone want to explain what this means in this context? Like, what are we saying here? Yeah, what are your thoughts?
We're saying that the expected value of this Poisson distribution is lambda, and that's because someone who's started making a lot of calculations and discovered that on average, like these Poisson distributions, their expected value is equal lambda. And so we can use that shortcut to find their expected value.
Yeah, exactly. So the idea here is we have a random variable, it's called x. It's distributed with a certain distribution. That just means if you look at realizations of this random variable, it has a certain shape to it in terms of what's likely and what's not likely. And the expected value of that random variable here is just equal to lambda. That's something that we could derive. It's it's something we could all do together using things that we've already covered. Or you can also look up some of the properties of different distributions in these tables. So we have various books and other things, resources, where it actually states, for each distribution, what are its key properties, what are its key parameters. So that would be another way you would know this. And maybe that'll be something we talk a bit about in the problem sets too, to get continued experience. And then the last question, does someone want to, maybe we should do this step by step. So does someone want to say what d-norm does? What is d-norm? Yeah, I heard it. What? Density. And can you say a little bit more?
So it's calculating the density of the normal distribution.
Exactly. So it's calculating the probability density, PDF, of a normal distribution, which is exactly what you would use in question 1 to calculate this quantity. Little p. Remember, little p usually stands for like probability density. Capital P often stands for probability mass function. There's a subtle distinction. And then we have p norm, which is, what does someone want to say p norm? What's p norm do?
CDF.
Yeah, exactly. P norm is CDF. And then what about R norm? You've used that one so much. R norm?
Random draws.
Exactly. Random draws. And then what about Q norm? The newest.
Inverse.
Yeah, exactly. Inverse CDF, also known as AKA quantile function. These are the 5. And for every distribution, you actually have those 4 things. Whether it be Bernoulli, binomial, or whether it be T distribution, Cauchy distribution, inverse Cauchy, it could be anything, but it's still going to be relevant. So those are a few thoughts about the quiz. I'm glad that you had a chance to test yourself. And there may be some things that you thought you understood that maybe you're feeling less certain about. That's actually a good thing because now you can go and review it and we can work together. We changed the office hour time, so the new office hour time are right after class on Wednesdays for me. For Andres, they're the same, but for me, they're right after class on Wednesdays. So just we can walk over. We either meet on the second floor porch or in my office, and we can talk about it. So that is that. So what we're going to do now is we're going to close the slides, and we're going to pull up the code, and we're going to talk a little bit about implementing the ideas that we discussed. And we have about 20 minutes or so. If we end early, that's fine too. So I'm not sure how long this will take. It'll be an experiment for us. But we're actually going to talk a bit about calculating variance from data, since this isn't a course on just abstract probability theory. And this also isn't just a course on data science. This is a course on integrating the probability theory together with the applied research problems so that you can get a head start on your research problems. Since the papers, there are papers that you need to write, there are ideas that you need to explore, and we're trying to at least provide some tools for you to explore them. So we're going to go through calculating variance from data, and we're going to use the Gapminder data, which is saved in that Gapminder package. That package is something you can download using the install packages command. And we're basically going to say, give me the data and save it as my data. That's what we have here. So this is the package, and we're extracting this function. We're extracting this data from that package, I should say. And based on the definition of, let me just make this a little bit up. Based on the definition of variance, and based on the definition of the mean, we can calculate these things. We can calculate first the first moment. So remember, we talk about different moments, like the first moment, the second moment, and we had different varieties of them. We had the raw moment, we had the the centered moment, and then we had the standardized moment. So now let's just compute the first raw moment, the empirical estimate for the first raw moment for South Africa in terms of life expectancy. So we're taking the data from South Africa, we're extracting the data from South Africa, and then we're extracting the life expectancy value for it, and we're just saying, what's the mean? This is our estimate for the first raw moment. We're going to be a bit more formal later on, what we mean by an estimator, what we mean by this, what we mean by that. But for now, basically, we're taking the mean of the data for South Africa, and that's the first estimate of the first raw moment. We can take the exact same thing for, South Africa, for the data for South Africa squared, taking the mean of that. So what this is approximating is the expected value of, x squared. We're basically just taking all the data, we're squaring it, and then we're taking that kind of averaging approach that we discussed. This is not theoretical, this is empirical. So remember, there's always this distinction between the theoretical quantities and the kind of estimates from data. This is a theme that will come up a lot later on too. But we take the first raw moment, the estimate of it, we take the second raw moment, the estimate of it. And now using some of the ideas in R, we can compute what's known as the plug-in estimator for the variance. Whenever you hear the word plug-in estimator, just think I'm replacing all of these E of x's with means and using empirical data. So plug-in basically just means replace the expectations with means using the data that you have at your disposal. And this is our first estimate for the variance of the life expectancy for South Africa. So remember, we don't just have 1 year of data here, we have actually multiple years of data. So we're asking ourselves, what's the variability around life expectancy for South Africa in the sample that we have? So the average life expectancy is 53 years for South Africa. It's not, that's what it is there. And we might ask ourselves, are there a lot of fluctuations around that average, or are there not a lot of fluctuations around that average? And the variance and the standard deviation too are one way of computing that, of answering that question. So now we're taking the data for South Africa, and we're following the formula. We're taking E of the mean of this difference, the mean of the square difference, and we're computing it. And we're computing it using the observed sample. So this is using ideas that we talked about regarding plug-in estimators, and that's what we have there. So we have the mean. We have one mean here, and we have one mean here, just like we have one expected value symbol there and one expected value symbol there. And we're taking the square just like we have the square here, and that's what gives us our first estimate of the variance. That's what we have there. So the estimated variance is 27. So if we took that and took 0.5, we get 5. So this is basically saying the average square deviation from the mean life expectancy across different years in South Africa is equal to about 27. And if we take the square root of that to get back on the original scale of the data, basically undoing the square operation, we get about 5. So that's some intuitive notion for the variability of the data. It's being captured in this notion of standard deviation. So this is the standard deviation, and this is the variance estimate for the data here. So that's what we have there. It turns out that we can also use this other idea, which is a simplification of what we had before. So this might be a problem in the next problem set, depending on how I'm feeling or how Andres and I are thinking. But one idea behind the variance is that we can take this more complicated formula, which was this thing, and we can actually decompose it into something even simpler, which is the following. We just take the expected value of x squared, and we subtract off the expected value of x, squaring that, and that quantity is actually the same as the quantity up here. So in other words, the variance we can think of computing it in several different ways, depending on what might be easy to do or what might be hard to do. So whenever you're doing some kind of analysis, it's always good to have options. And this is one option you have at your disposal. And we'll talk about that in the problem set, and we'll talk about that continually throughout the course. But the idea is, instead of computing the expected value, the variance in this way, you can compute the expected value in this other way, and it turns out the two are identically the same. So it's not that they're approximating each other, it's that they're identically the same. I haven't given you a proof, so to speak, or an explanation, so to speak, of that, but we're going to show it now by just saying, by computing the variance in this other way, and it's basically taking the second raw moment and subtracting off the first raw moment, squaring it, getting another estimate for the variance, and it turns out that the two are the same here, and they should be the same theoretically. The two are equivalent. So this is another way of computing the variance, not using the expected square deviations directly, but instead computing the expected square deviations in a proxy manner using the raw moments and proceeding in this fashion. So this is just an introduction. Yeah, question.
What is that AL means?
Oh, sorry?
What is the AL in the run function?
Oh, 8L. Yeah, good question. So this is just, so remember how when you're all becoming, expert computer programmers, hackers in training, so to speak, and remember how there are data types. There is an integer, there is a real number. We have different data types in R. R isn't a strongly typed language. In some languages, you really need to specify everything you do, like what is the data type, what is the data type, what is the data type. That's generally a more secure way of writing your code, less prone to error, less prone to bugs. But R is pretty flexible, but you can still explicitly state what type the different objects are. So when I do this, and I do class, the class of 1 period is going to be numeric. The class of 1 is also going to be numeric by default, but the class of 1L is actually going to be integer. So by putting that little L there, I'm saying make this explicitly state that I'm explicitly telling the computer that this is going to be an integer that I'm passing it. This isn't important most of the time. I wouldn't worry too much about it, but that's what's happening here. So when I'm rounding this difference, theoretically it should be 0. Just based numerically, it's not 0. But the reason I have this 8L here is I'm saying round this to 8 decimal points, and when I do that rounding, that 8 is an integer. That 8, it'll still work if this is a period here, but technically speaking, this numeric quantity is being coerced into an integer at some level. So I just like, for my own understanding, I like to usually explicitly say like what's an integer and what's not an integer. Just for my own understanding, it's not super important, but that's what's happening with that 8L. We're rounding to 8 decimal points, and that 8 is an integer, and that's what the L is doing. Good question. Other questions? Anything else that you're looking at this and you see this doesn't make sense or that does make sense? Anything else in the code that looks either like it makes sense or doesn't make sense? Yeah, question.
Can you explain the difference between line 16 versus line 17?
Yeah, good question. So there's line 16. So this is computing our other estimate of the variance, and then in line 17 we're computing the difference between our estimate from up here and our estimate from down there. So this is another trick for everyone. When you're in RStudio and you highlight something, all the other times you've used that object get highlighted. So I'm looking at it and I see that it gets highlighted up here, whereas when I highlight 1B, it's highlighted there. So I can kind of visually inspect the code and see where is this occurring, where is this not occurring. Good question. Other questions, other comments? Okay, I think we have about 5 more minutes together. So this is good. We're going to end roughly on time, I think. It turns out that this way of computing the variance has a slight degree of bias. The bias gets really small when your sample size is really big, but nonetheless there is a slight degree of bias. There's a way to debias things. I'm not really going to explain that now, but as a way to presage what's to come, just note that the variance function in R is going to give you a slightly different answer than that quote-unquote naive calculation, just taking empirical means using the quote-unquote plug-in estimator. So if I use R's variance function, it looks a little different. That's actually a pretty big difference between what we did before. 29 versus 27. That's a pretty big difference. And the reason is there's a slight adjustment for what's known as a finite sample bias to this original approach using the quote-unquote variance estimator, plug-in estimator. So that's just something to keep in mind. In general, using the plug-in function, using the built-in R functions is going to be the way to go. But I wanted us to just physically compute the variance using the plug-in method so that you can at least try to gain some intuition for what is happening, what is happening, what is happening. So that's one comment about that. It's I'm kind of introducing today's session. It's a little bit of there's a lot of presaging for today's conversation. So there are some words that I'm saying that maybe are going to be unclear, but that's because we're going to talk about them on a continuing basis. Okay, so now I want to compute the variability in life expectancy, not just for one country, but actually for all countries in my entire sample. I could use a for loop for doing that. I could use like a group by function that maybe Andres will talk about using dplyr and so forth, but I want to use a function called tapply which is basically going to take the first input. So this is the first input. It's going to take all of my first inputs, and it's going to compute some function that I've defined on the right-hand side, broken up by the different values in the thing, in the second thing. So this is sort of a confusing function, but I think it's x. Is x the input? This is a function that takes a while to really master, and I think that's why I'm bringing it up now, because we're mastering it starting now together. But the basic idea behind this function is, the basic task that I'm trying to solve is, I want to do some subgroup analysis. In this case, the subgroup analysis that I want to do is I want to compute the variance, because some countries will have a high variability in life expectancy and some will have a low variability. And I want to understand, what is it about the high variability, what is it about the low variability countries, and how can I build a social science theory on that to learn more about the world. And the tapply function does just that. You take your input data and you break that input data down by the different values in the country in the second thing, and then you apply some function to the inputs defined here, broken down by the things defined there. So it's a bit of a mouthful, but this is what it is, and I'm showing you this too. One thing I like about dplyr is it makes something like this probably a little bit easier, but one reason I like the tapply way of doing this is that you can write more general functions using tapply. Like this function that I have here, it could be some crazy thing like variance squared divided by the mean of x or whatever. It could be some crazy thing and it'll still do it. Whereas with dplyr, it's more of a built-in mentality where there's a more restricted set of functions you can do. Whereas now we're going crazy with any function. Like this could be, some crazy neural network that you're training somewhere. It could be anything. And that's also another motivation for learning a little bit about functions, for learning a little bit about what they do, for learning a little bit about how to write them, and that's what we're doing now. We've written a function, and the function is the third input to this other function, the tapply function, and together this calculates the variance, the country level variance, broken down, like by country, like I said. So this is what we get, and just to show you the results, we can look at it, and it looks like Oman has the highest variability in life expectancy. Saudi Arabia has a high variability, Indonesia has high, Vietnam has high. So we've sorted the data using the sort function. And it looks like the lowest variability is actually, I think it's Denmark. So low variability is coming from places like Iceland. Well, we can use head to look at the first 6 observations. Head looks at the first 6. It's Denmark, it's Liberia, it's Norway, Netherlands, Hungary, Slavic Republic. And then we can look at tail to look at the last 6. It's Yemen, Indonesia, Saudi Arabia, Vietnam, Oman. So I think the basic story here is that there are 2 general tendencies. If your life expectancy is going up, the variance is higher just based on how variance is calculated, or when you're in a very unstable place and conditions are either good one year or bad the next year, you're also getting a really high variance. Whereas you're getting low variance in places where the life expectancy stays really low or stays really high. So that's the explanation there. And it looks like we have like 1 minute. In that last minute, I just have us go through writing data in R. I have a little tutorial here for you, so if you want to take a look, you can experiment with it. But I show you here how to write data in R using the write.csv function using paths. So paths are something that, especially if you use like a Chromebook, probably is pretty unfamiliar to, but you're going to get to know paths because they're really useful for reading data and for writing data. The basic idea is I'm specifying where on my computer I'm saving this data with this particular name. So gapminder.csv is the name that I want to specify. This is the data set that I want to save, and this is the location. Everything up to here specifies the location of that data. In a lot of the operating systems that you'll use, this tilde specifies the home directory, which basically is like the starting point in your computer. So your computer is it's structured like a kind of like a tree where you have the base of the tree, and then you have different branches representing files. Within each branch, you might have sub-branches representing sub-files and sub-files and sub-files. So in my downloads directory, I'm going to save this particular data set. I could do that in another way using by setting my working directory, which basically tells my computer every time I specify a path to save something or to read something or write something, start here and then branch from there. So if you think about it like a tree, you're basically saying, here's your file system. You're basically saying always start from this location in the tree, known as the working directory. And in this case, that branch is set to downloads. And that basically says always start looking for things here, and always, by default, read and write starting there at that location. And this is just something to keep in mind. I think that this is one of the more confusing things in R, which is why I haven't talked about it until now. But when I first learned R, it took me a while to get that down. It's like, what is this directory, working directory? But just think about it like a tree where each branch represents a folder, and the working directory is basically where your computer by default is going to look for files within this tree. And I have a little note on the bottom that when you're writing your R scripts, it's generally good practice to use the relative paths using the set working directory functionality, because then it makes it easier for your neighbor to reproduce it. All they have to do is set the working directory once at the top of their script, and then they can just go plug and play. They don't have to rename all the paths later on. So I think I should stop there, but we have a little bit about reading CSVs too. Definitely go through that on your own time, because in the problem sets it's important, and obviously in your future research it's going to be important too, and so forth and so on. So we'll stop there. Thank you all for your attention, and we'll meet again on Monday.